In this video, we're going to talk about the technique of integration by substitution. All right, so integration by substitution, it's a method for computing antiderivatives or integrals, right, that involve the chain rule. So for instance, let's take a look at this first integral here. We have the integral of cosine x dx, and that function, right, there's no substitution needed. If you take a look at this function, right, cosine x, to take the derivative of cosine x, right, it wouldn't require the chain rule, right? And so it's pretty much the same thing for the antiderivative. I want some function whose derivative is cosine, right? And that would be just sine of x plus some constant c. So for this integral, there's no substitution needed at all. Next up is a slightly different function. Right here we have cosine of 5x. The only difference is that there's a 5 right inside the cosine. And on this one, this is one where you might want to use substitution, although in terms of integrals that you can use substitution on, right, this one is not that complicated, but it is one that you can use substitution. Notice if I were going to take the derivative, right, of cosine of 5x, that would involve the chain rule, right, because the inside part is not just x, but something more complicated than x. So likewise, when I go to take the antiderivative, I'm going to have to take that chain rule into account, and that's what integration by substitution does for you. So let's take a look at these two integrals. We're going to compute this one, of course, that's basic, one of the basic facts really. Then we're going to compute this one without using substitution, and then we're going to compute it using substitution, just to give you an idea of what the substitution method is all about. So here we have cosine of x, right? We just want some function whose derivative is cosine, and we all know that that is sine of x. So the integral of cosine of x dx is going to be sine of x plus some constant c, and that's all there is to that one. So no substitution needed, nothing else. But we'll see, right, that the problems that do involve substitution, they're going to take into account these more basic integrals. Basically, what substitution will do is take a complicated integral, right, and kind of reduce it down to a simpler one like this. All right, so now here is the integral of cosine of 5x dx, and we're going to do this one without using substitution first, and then go back and rework it with substitution. All right, so without substitution, basically what you would do is use that fact that we just looked at, right? The fact that the antiderivative of cosine is sine, or the integral of cosine is sine, however you want to talk about it, to do this fact. So I usually call this method the guess and check method. I'm going to guess, hey, well, the integral of cosine x was sine of x, right? So why wouldn't the integral of cosine of 5x be sine of 5x plus some constant c? And it's going to turn out that, well, because of the chain rule, right, it's going to make things slightly more complicated than just putting 5x in for x there. But so that's what my guess is going to be. And that's not a bad guess, but if we go to check that guess, right, if this is a correct guess as to this antiderivative here, or integral, when I take the derivative of sine of 5x plus c, I should wind up with cosine of 5x. Okay? All right, so I'm going to take the derivative, right? This is a chain rule problem, so I'm going to take the derivative of the outside part, which is cosine. I'm going to leave the inside part alone, and then, right, the third step of the chain rule says you need to multiply by the derivative of the inside part. The inside part here is 5x. The derivative of that is 5. So you can see that little 5 pops up in there. And of course, the derivative of any constant is just 0. So when I go to check, I get that the derivative is 5 cosine 5x, not cosine 5x. So you can see that I wasn't far off, right? I'm only off by that factor of 5 right there. Okay, and that's easy to fix. Okay, so there's no real shame in guessing incorrectly, right? But you need to check, right? And then you need to alter your guess, right? That's where the real work comes in. Okay, so I'm going to adjust my guess to 1/5, right? Remember I had a 5 in there, and when I checked, I didn't really want that 5 in there. So I'm going to put a 1/5 out in front, okay? And because of the way that the constant multiple rule works, right, I can it will get rid of that 5 there for me. So when I go to check, right, I'm going to use the constant multiple rule. The constant multiple rule says rewrite that 1/5, right? That 1/5 is a constant, so I have a constant times a function. So rewrite the 1/5 and multiply by the derivative of the function part. So again, the derivative of sine 5x is a chain rule problem. I am going to take the derivative of the outside, leave the inside part alone, and then multiply by the derivative of the inside part, right? Just like we did before. And now you can kind of see what happens. That 5 and the 1/5 right here are going to cancel each other out and leave me with cosine of 5x, and that is exactly what I wanted to see, right? That tells me that the antiderivative of cosine of 5x is 1/5 sine of 5x plus c. Or in other words, right, this statement right here, okay? So that's what I call usually the guess and check method. After a while of doing these integration by substitution problems, right, you can almost kind of look at the simpler ones like this one and kind of tell what the answer is going to be. If you know the basic antiderivative facts and practice doing these integration by substitutions. In fact, in Calculus 2, that's kind of the level that you need to be at, where you can kind of look at these simpler ones, simpler in the big picture. Right now, they probably seem a little bit complicated, but once you keep progressing through these ones, you can almost look at these and kind of tell what the answer is going to be. Okay. So next we're going to use the substitution method to compute this exact same integral. And so hopefully you can kind of see some of the parallels involved in there. Okay, in the substitution method, right, you're going to pick u, right, is generally the variable that is used, although you can use whichever variable you like except for the original one here. All right, so I'm going to pick u equal to 5x. So generally speaking, you pick u to be some part of your integral here, and a lot of times it's going to be the inside part, like this. Okay. Next up, you're going to do what's called calculate du. So what you're going to do is take that u that you picked right here and just take the derivative of both sides. Okay. The derivative of u is 1, right? And then we're going to attach this du right here. Okay. A lot of students, when they first see the integration by substitution method, have a lot of questions about the du. What is it? How does it work? The way to think about it is that it helps you to kind of reverse the chain rule process there in a more mechanical way. You don't really have to think quite as much about it as you do in the guess and check method and how that would work. Okay, so just whatever your substitution is, take the derivative of both sides. So the derivative of u is 1, and then put du here. Multiply that by du. The derivative of the right-hand side is 5x, okay? And the derivative of 5x is 5, and then tack on this dx here, okay? And so, and then hopefully you'll see in a minute here how we use that du and the dx. Okay, so now what we're going to do is make the substitution. We're going to use this equation here, the u is how I usually refer to that, and du, this equation right here, to change all of the x's to u's. All right, you don't get to like change some x's, right, and leave some x's and change some to u's. Every instance of the variable x in the problem must be changed to a u. So that includes this x in here, right, or 5x in here, and this dx also, right? So that's kind of what the dx and the du function to serve as, right? They tell you how to switch the dx over here to du. All right, so many times what you're going to have to do is adjust the u and or the du, right, to make the correct substitution. Looking at our problem right here, we can see inside here we have 5x, and that's exactly equal to u. So that part is generally easy, and that, generally speaking, is one of the easier parts of the substitution. You're going to pick u to be equal to some part of your integral in there, and that part that you picked is just going to be changed over to u. So that part's easily accounted for. Then dx over here, right, is the only other x that occurs in this problem, right? And I can see right here that I have 5 dx. I don't really have that 5, right, any other place outside. I have it right here, but I'm going to use that to switch over to u. So what that means is that in this problem, I'm going to have to adjust this formula right here. I'm going to have to adjust du to make it fit the problem. Okay. All right, so du equals dx. I noticed in my problem that I only have dx in there. And so what I'm going to do is multiply both sides of this equation by 1/5. Over on the right-hand side, 1/5 times 5 will cancel each other out and give me a 1. Okay, so now what I have is dx exactly equal in terms of u over here. Notice, right, there's just x's over here and there's just u's over here. If your du is off by more than just a number or a constant right there, then that's not, generally speaking, a good sign. And it may be a more difficult substitution problem, or maybe some other technique that you want to use on the integral. All right, so now we're ready to make the substitution. There is the original problem that we had, and what we're going to do is we're going to make that substitution. So right here, this 5x, right, that was what we picked u to be. U was equal to 5x. So I take this 5x inside here, I switch it to u. Okay, then that leaves me with this dx that I need to account for, right? And up here you can see that dx is equal to 1/5 du. So I took this dx over here and substituted in to 1/5 du. All right, so now you see every single instance of x, right, has been switched over to u's. I didn't leave some x's in here. There's not mixed x's and u's in here. I accounted for every single x, and every single x has been switched over to a u. So that's what you want. Here I have a constant, right? That constant can be pulled out according to the rules of integrals here. That's just the constant multiple rule for integrals, right? And so that leaves me with this integral cosine of u du. So notice how that integral now is one of the simpler ones. It's exactly the same as the simpler one that we started with, right, except for that 1/5 out in front. So taking a look at what we've got, 1/5 times the integral of cosine of u du, right? One thing that you should note, right, at this point, the new integral that you get, right, the one after the substitution, that one should be simpler than the one you started with. And if it's not, right, then that's a sign that you picked the wrong u, most likely. And again, there's no shame in that, picking the wrong u, right? But what you need to do is just go back to the beginning, right, and pick another u, try another u, and see if that works, okay? All right, so now we're at the point, we've got an integral that's pretty straightforward, right? And so we just integrate it. So we have 1/5, and some function whose derivative is cosine, right, is just sine of u plus some constant c. Okay, so now we've got the integral, but it's in terms of u. What you're going to need to do then is to go back and back substitute, right? We know that u is equal to 5x, so now we're going to switch all the u's back to x's, right? And since u is equal to 5x, we can just put 5x in place of the u. And now we have our antiderivative, right? The same one that we got the other way, and so it's exactly the same. So you might think, well, it seems like quite a few steps to integration by substitution, right? And there is, right? But in some of the more complicated problems, right, this is definitely the way to go. In the simpler problems, maybe the guess and check might be a little bit easier to me, especially as you start to gain more experience working these problems. Okay, just to recap the general steps for integration. Number one, identify the problem as an integration by substitution problem. So this would be similar to the chain rule type problems. we have some basic antiderivative or integral facts, right, that you need to know from the previous section. And the integration by substitution problems would be ones where the inside part basically is more complicated, or ones where the basic facts don't apply. You're going to pick u, right, as to be some part of your integral. And in a second, we'll talk about what are some good choices for u and some bad choices for u. The next step is to calculate the du, right? And then make your substitution and adjusting the u and or the du if necessary. And the easier problems, really, it's just the du that you'll have to adjust. In some of the more difficult problems, right, it might be both the u and the du. Step 5 is to integrate, right, and then back substitute, switch back to the original variable. Okay, so that's how the general outline of the steps for integration by substitution. All right, what are some good choices for you? The most, probably usually the best choice for you, although again, not always, you can't say this always works, but the inside parts of the function, right, are probably a good choice for you. That's one to try if there's nothing else obvious in there. Okay, the other thing is parts of the function whose derivative or almost appear or appear as a factor in the integral. So in other words, if you have x cubed or something, and then in the integral you see 3x squared in there somewhere, then that's probably a good sign that u, especially if the x cubed is inside of another function, that you would pick u to be x cubed. And it doesn't have to be exactly 3x squared. That's why I say almost. It could be x squared or 5x squared or 7x squared, where it differs by a constant, right? Because you can adjust your du, and so the constant part of it really doesn't matter that much. If you don't see anything like parts 1 or 2, then the denominators of the function in the integral might be a good choice. So the bottom part, right, of a fraction in there. Exponents of exponential functions. So if you have e to some other function of x in there, that exponent part might be a good part to choose to be u. And then parts of the integral that you don't know how to integrate, but you can take the derivative of. So examples of that would be something like natural log x, right? We haven't talked about how to integrate or the antiderivative of natural log of x, but we do know that the derivative of natural log x is 1 over x, right? It's the same thing for inverse trigonometric functions. For instance, we don't have anything that tells us what the antiderivative or integral of the tan inverse function, right, is, but we do know that the derivative of the inverse tangent function is 1 over 1 plus x squared, right? So those would be good choices for you in the problems there. And as you look through the examples and work through the problems, you'll kind of identify which parts are good choices for you. Some bad choices for you that you should never really make. Number 1, u equals x, right? Don't bother wasting your time, right? If you can do this, right, and calculate du to be dx, but then when you replace all the x's with u's, you'll have exactly the same integral that you started with. So that's never really a good choice. And then the other thing is u equal the entire integral, right? If you can set u equal to the entire integral, right, and compute it, and it works out, well, what that means is that you didn't really need to use integration by substitution in the first place. So if you find yourself doing these two things, then you really don't want to do that. All right, and that's about it for integration by substitution. We'll take a look at a few examples of how that goes after this.